Hello, everyone. Welcome to matrix multiplication. If there's one operation that is trickier to learn, it is indeed matrix multiplication. But let's jump right into it. So, what is the multiplication of two matrices or matrix multiplication? So, first, now you're going to start with two matrices, A and B, for the actual product to be defined, for the matrix multiplication to be defined, the first matrix, A, suppose the size of that matrix is m by n, so m rows and n columns. And then if you look at B, that matrix B needs to be a n by q, so n rows and q column. So here it is absolutely essential that the number of columns of A, the number n, is equal to the number of rows of B. This is the requirement for that operation to be defined. So how do you compute that matrix A times B? Well, first, the product between A and B is a matrix that I'm going to call C, and the size of that matrix is actually a M by Q, in the sense that if you know that your matrix A has M columns, and you know your matrix B has Q rows, the product of AB will be a M by Q. And how do you compute the entry on the ith row j column? The trick is to first construct a vector. A vector is just n numbers together. So a vector in our n just means I have n numbers. And where are these n numbers coming from? Well, they're coming first from the ith row of A. So you take the ith row of A, that will be n numbers in our n. And then the second vector will be bj, a vector in our n. So again, n other numbers that you get by extracting the jth column of B. So the entry on the ith row of your product and the jth column that I'm going to call Cij is the dot product between AI and Bj. If you don't remember how to do a dot product, don't worry. I'm going to do a lot of examples in a moment, but just a quick example. For example, if I have 1, 2, 3, so a vector in our tree, dot the vector, let's say 1 minus 1, 0. The way you compute this dot product is simply by going, you take the first number of the first vector and you multiply it with the first number of the second vector. So it's 1 times 1. So you get 1 times 1. Then you go plus and you multiply now the second entry. So 2 times minus 1. So you get plus 2 times minus 1. And then you add the product of the third entry. So plus 3 times 0. So plus 3 times 0. And you get 1 minus 2 plus 3. So in this case, you get minus 2. So the product that you get, or sorry, the entry that you need to construct is the result of a dot product between the ith row of A and the jth column of B. So we'll do examples, but again, I want to really put an emphasis on this formula, but the best way to learn how to multiply matrices will be by looking at examples. So just one small remark before jumping into examples. So the trick I'm going to use to do products, and this is the trick I'm going to use all the time, every time I want to multiply A times B, where the number of columns of A are the same as the number of rows of B, is I will always, for the first matrix on the left, so typically A, I will always circle the rows of the left matrix A, and I will circle the columns of the matrix B. And again, the Cij being the dot product between the ith row and the j column is the following. So you extract row I of A and you do the dot product with column of J. And because row A in general will be a vector where these entries in the vector are all the entries on that matrix A in general, and then the entries for the second vectors are the elements of the jth column of B, and then you do your dot product, your A I1 times B1J plus A I2 times B2J plus etc. And then you just add the last product of the last entries together, A, IN, B, and J. Again, a lot of terminology and notation here. Let's just look at some examples and let's apply these tricks with concrete numbers. Again, in this chapter, the trickiest operation to learn is matrix multiplication. It's not that hard, but it's one of those things. If you know, you know. If you don't know, you don't know, and you're missing out something. All right, let's do an example with numbers. So, my example that I want to go through is compute if possible or if defined A times B times A times and C times A for the following matrices. My advice, if you have to do matrix multiplication, is to always write the dimension of those matrices. So, for example, for A, I can see that this matrix A is a 2 by 3. So this is an example of a 2 by, I said 2 by 3, I suck, 2 by 4. So we have a 2 by 4 matrix for A. For B, B is an example of a matrix that has 4 rows in one column. So it's a 4 by 1, also known as a column matrix. And then the last one, there's 4 rows, 2 columns. So that's an example of a 4 by 2. So write your dimensions because we're going to be using the dimensions to check if the product is first and foremost um, defined or not. So let's start with A times B. So is this product defined? So my advice, I already have the dimensions written down. A is a 2 by 4, B is a 4 by 1. So what you're looking for is these inner numbers, the 4 in the 2 by 4 and the 4 in the 4 by 1 are equal. So I know that this matrix is going to be defined. And not only that, I also know if you look at the outer numbers, so the 2 by 4, if I look at the 2, I know that the row number of the product is going to be a 2, and the column number of B is going to be the column number of your product. So your 2 by 4 times a 4 by 1 will be a 2 by 1. So I already know the dimension of my product. All right, now that my two matrices are next to each other, I'll show you how I like to compute the actual resulting product. So again, for me, what I like to do is I really like to circle the rows. So I circle the rows of the left matrix. So I have 1 and 2 rows of the left matrix A, and I circle all the columns. There's only one because that's my first example, all my column of my second matrix. And you can also double check that way if the product is defined because you can see here in all those rows and columns that I've circled, all of them have 4 entries. And I need those numbers to be the same so that when I do my product using the trick that I like, I have a match between these numbers. And how do you get the actual computation? So for me, I like to think about the column that I have on my in my matrix B, and I just take this column and it lays down on every row. So what I mean by this is I like to take that column and I like to rewrite those numbers on top. For example, I like to bring that column down and say, okay, so that column is falling down the 4301 minus 1. So I like to write the 430 minus 1. And the way I get my first multiplication, that dot product here, is the first number that I'm going to get in my computation is minus 1 times 4. And this is what that minus 1 times 4 is, plus 0 times 3, plus 1 times 0, plus 2 times minus 1. So in my definition, when I say the dot product between row 1 and column 1, this is what I mean. I'm thinking about the vector minus 1, 0, 1, 2, and the other vector 4, 3, 0, minus 1. And I do the dot product and I get this big computation for the first entry, first row, first column. I'm using the first row of A and the first column of B. Of course, there's only one. And then I just take that column now on the second row to compute the second entry on the second row. So here, I like to write my numbers nearby because I'm not smart enough. So I like to rewrite the 4, 3, 0, minus 1. And then here we go. Let's multiply. So here, 1 times 4 plus 2 times 3 plus 0 times 0 plus minus 3 times minus 1, and then I add everything up. And here, my resulting matrix has two rows because my original matrix has two rows, and one column because my original matrix on the right has only one columns. And then if you do the math, you're getting minus 6 for the first computation on the first row, and you're getting 13 for the second computation. And you can see again here that the final answer is a 2 by 1 matrix. So I know I've done my math correctly. All right, now let's try to do B times A. So for B times A, again, I like to put my dimension of my matrices next to each other. It's a 4 by 1 multiplying a 2 by 4. Uh-oh, my inner dimensions are not the same. Then I'm done with this question. Yay, it's undefined. The number of rows of B are not the same as the number of columns of A. That's it. That's all for that computation. It's undefined. Next example, let's try to compute A times C. Again, I like to put my dimensions of A and C respectively next to each other. 2 by 4 times a 4 by 2. The inner numbers are equal. Yay. And then my outer numbers, the 2 in the 2 by 4 and the other 2 in the 4 by 2, gives me a 2 by 2. So without computing anything, I know this product is defined and I know the dimension is a 2 by 2. So here we go. So again, for these questions, just take your time, just circle the right things in the right spot. So for me, I like to start with circling uh, by circling the rows of the matrix A, so the one on the left side, and circling the columns of the matrix on the left side, in this case C, and I see that everything that I'm circling contains four elements. This is another strong indication that my product is defined. So here in my computation, I have like all my focus is all on the first column. Me, I like to work one column at the time, working on the right matrix. So I take the 1 minus 2 0 minus 1 and I lay it down on my matrix A, and then I get my first product, minus 1 times 1 plus minus 2 times 0 plus 1 times 0 plus 2 times minus 1. So that's the result of taking the first column of the matrix C on the first row of A. And then that same row falls now on the second row. Sorry, the same column falls on the second row. And I have my 1 times 1 plus 2 times minus 2 plus 0 times 0 plus minus 3 times minus 1. And I took the time for that question to really color code all the entries so that you can see which numbers falls next to which one. Again, if you need to write these numbers, like if you need to, like don't be shy, like if you need to write the 1 minus 2 0 minus 1, so the 1 minus 2 0 minus 1 to better understand Where are these computations coming from? Do it. Okay, so, and actually here, if you do the computations, you're going to get minus 3, 0 for the first column of your 2 by 2 matrix. And then if you continue, so same idea now. So I still have my rows on A, and now I'm focusing on the second column. So I'm bringing that second column down. So the 2 minus 1, 3, 0, and I bring down, so I'm very lazy. I bring down the 2 minus 1, 3, 0. So that column 2 minus 1, 3, 0 goes down to every single row. And now when you do your computation, so 2 times minus 1, that's this one, plus minus 1 times 0, so minus 1 times 0, plus 3 times 1, plus 0 times 2, and then same thing on the second row, so 1 times 2, plus minus 1 times 2, plus 0 times 3 plus minus 3 times 0. And if you do this computation, you can verify that you get 1, 0. So your final answer is this nice clean 2 by 2 matrix, minus 3, 1, 0, 0. And that's the result of multiplying A times C. All right, the last example in that example, let's compute C times A. Again, write the dimensions of those two matrices next to each other to ensure that this product is well defined. So we have a 4 by 2 multiplying a 2 by 4. The inner numbers are 2. The inner dimensions are 2, so they're equal. And then the outer numbers, the 4 and the 4, gives you the dimension of your matrix. So your answer is going to be a 4 by 4 matrix. So the product of this matrix multiplication, the result of this matrix multiplication is a 4 by 4 matrix. I'm not going to go over all the detail. Again, I took the time to color code all those computation. I'm just going to show you the result or the way you do the operation for the first column of A, and then you can just rinse and repeat for the rest. Again, so here for me, when I'm doing these questions, I like to circle. It's already done here for you using colors. I'm just going to trace over just to really see it. So I like to circle my rows of the left matrix and the columns of the right matrix. And you can see here that all the rows or the columns that I'm circling all contains two numbers. Another indication that my product is defined. Oh yeah. And now just to show you the the math for the first column. So for me, I'm always focusing on columns going down. So I'm just going to go through the operations of taking the first column down on each row. So I like to rewrite the minus 1, 1. I like to write it everywhere because I'm going to be using it in my head to compute. So here, when I look at my computation for the first column, I have 1 times minus 1 plus 2 times 1, and that's this operation right there. 2 times minus 1 plus minus 1 times 1, that's what's going on the second column, a second row, I'm sorry. And then for the third row, I have 0 times minus 1 plus 3 times 1. So this is what's going on the third row. And finally, minus 1 times 1 plus 0 times 1. This is exactly what's going on the fourth row. And if you do these computation, you're going to get 1, 1, 3, 1. And then you just move on to the next row and you take that 0, 2 down, and then the next column, the 1, 0, you take it down, and etc. And this will give you the computation needed to fill out the computations for the second, third, and fourth column. And you can see at the end, you get this nice box, which is a 4 by 4, which was already predicted from the um, the dimension analysis from your product. Not only do you know if it's defined, you know the size of the matrix that you get just by reading these dimensions. All right, that's it for that example. I know you want more, so here's some more. So next example, let's compute AB and BA if possible. So if we start with AB, so AB is the first one I'm going to check. So again, small dimension analysis, 2 by 3 times a 3 by 4. Those inner numbers are equal, and the outer numbers gives me the dimension of my matrix. So I'm building a 2 by 4 matrix. As you can see here, my rows of matrix A and my columns of matrix B are already circled, or here I'm just using a highlighter, and I can see that all the rows and the columns that are highlighted, they all have 3 elements. So if I do my computation, again, I'm a row person, so I like to focus on, sorry, I'm a column person. So I start on 402. So again, here, the trick is I am computing 4 times 1 plus 2 times 0 plus 4 times 2. That gives me, so using the first row of A and the first column of B, you're getting the first row, first column element, and you can double check that this will add up to 12. And then 4 times 2 plus 6 times 0 plus 0 times 2. So when you take the first column down on the second row, you're getting the second row first column entry, and you can double check that this will give you an 8. And then again, so you move to the second column and you take that second column down. So if you take 1 times 1 plus 2 times minus 1 plus 4 times 7, that's this computation right here. And then again on the second row, 2 times 1 plus 6 times minus 1 plus 0 times 7. That's the computation on the second row, second column. So you're using the second column of B to build the second column of your product, row by row. And then you can verify that those two computation will give you 27 and minus 4 respectively. And then again, so a lot of rinse and repeat here. If you take the column 4, 3, 5, and you lay it down on 1, 2, 4, and 2, 6, 0, you can see that for the first row, third column, you're getting 1 times 4 plus 2 times 3 plus 4 times 5. And on the second row, third column, you're getting 2 times 4 plus 6 times 3 plus 0 times 5. And you can see you should double check that these computations adds up to 30 and 26. And then one more column. Okay, so now 3, 1, 2 is falling down on the first and the second row of A. So if you do the first row first, so you're going to get 1 times 3 plus 2 times 1 plus 4 times 2, which will add up to 13. And then for the second column, it's 2 times 6, 2 times 3 plus 6 times 1 plus 0 times 2. And you can double check that this gives you a nice 12. So again, this is the way I like to do it. Circle the rows on the left matrix, the columns, circle the columns of the right matrix, then column by column on the right matrix, lay down those columns romantically down to the rows of the left matrix, multiply these entries that align and add everything up. That's the same thing as saying you're doing dot products between rows and columns. That might be too much, but that's what's going on with that question. Now for the product B times A, this is an easier question because when you put B and A next to each other, it's a 3 by 4 multiplying a 2 by 3. The inner numbers are not the same, and because they're not the same, this operation is yay undefined. So a nice little remark here that comes for free to some extent. We did the computations to get A times B, and we got a nice 2 by 4 matrix. So A times B was a nice 2 by 4. But meanwhile, B times A was not even defined. So one thing to remark here is that matrix multiplication is highly non-commutative. We're used to 2 times 5 is equal to 5 times 2. But for matrices, sometimes in one direction, A times B is defined. Like in here, we have a nice fat 2 by 4. But the other way around, you're not even getting something that is defined. So AB is not equal to BA in general. So very, very, very different behavior when you permute the order of multiplication. So be aware of that. The next example is going to be done very quickly, but I want to still put an emphasis on that definition, like taking the row I and the column J, because sometimes in evaluation, we might be asking you to compute the product, but we're only going to be asking you to compute one entry. Like for example, here, let's compute A times B and B times A if possible. Let's get the one that is obviously not defined first. So B times A, if you're trying to compute B times A, B is a 3 by 4 matrix. You can write the dimension here, 3 by 4. And meanwhile, A is a 3 by 3. So you see the middle numbers are not the same. So bye-bye. Okay, no product to do here. So this operation is undefined. But meanwhile, if you look at the other one, the A times B, A is your matrix, which is a 3 by 3, and B is your 3 by 4. So I know this product is defined, and I know the size of my answer because these middle numbers are equal. The other numbers tells me my dimension of my product, which will be a 3 by 4. So I have the answers for you. It's a good exercise, of course, just to do it. Again, I strongly suggest that you circle the rows of the left matrix and the columns of the right matrix. And you take all these columns one by one and you just make them fall onto the rows to compute your outputs. But I just want to show you one specific example. Suppose we want to compute the entry, let's say the one C23. How can you compute this entry without computing the full matrix multiplication? Of course, if you have the full matrix multiplication, you can see that the entry on the second row, third column is minus 68. But how can you do this without multiplying everything? Well, if you want C23, what you should do is take the second row of your first matrix. So the first number tells you which row to pick. In this case, it's minus 4, 5, 7. And the 3 tells you to use the third column. So you take the third column. So those are the only two columns that you need in order to do your computation for the entry C23. So like the definition, so if you are trying to compute C23, what you're doing is you're using row 2 of A, and that's minus 4, 5, minus 7, and you're using the third column of B, and that's 2 minus 5, 5. And then you're doing your dot product. You're multiplying minus 4. So minus 4 times 2 to get your first entry, plus 5 times minus 5, plus minus 7 times 5, and you get your minus 68 directly. So you can get that minus 68 simply by doing the dot product between the second row of the matrix A and the third column of B. So one small multiplication between two vectors, a dot product between two vectors, and you can get minus 68. Because yes, on the test, if I ask you for the entry two threes and you do the full computation and you get your matrix like fully computed, and then you extract the right entry, that will work. But this is 12 computation versus 1 if you just use the definition. Take row 2 dot column 3 of matrix A and matrix B respectively, and you can get your minus 68 right away. One last example, just I want to illustrate again that product is not commutative. you could have the impression that my earlier example, when I said that B is not equal to BA, was because the BA was not even defined. Well, here I have an example where not only is AB and BA defined, but both of them have the same dimension. But even in that case, the results are different. So I have a 2 by 2 multiplying a 2 by 2. So both operations are defined. AB, if you put the dimension next to each other, 2 by 2 multiplying a 2 by 2, the inner numbers works for both, and both of them will be 2 by 2 matrices. And here as an exercise, do it. So AB and BA, make sure you always circle the rows of the left matrix and the columns of the right matrix. And if you do your multiplication correctly, you will see that these two matrices, AB and BA, are not equal. So even if both of them are nice 2 by 2 square matrices, their entries are not the same, and the product is not commutative, even in the case when they're both defined, and even in the case when they're both have the same dimension. So that remark in general, AB is not equal to BA. All right, for that section, and again, this section is the trickiest one for that section. That's it. That's all. Make sure you practice, les amis. So that's it. That's all. Bye bye.